there's going to be a lot of details on scalability because it's quite a big topic. Uh, it's a problem or rather a solution available across industry, right? So we'll be focusing mainly on software and then how do we scale on web applications as such. But then we'll start with a few examples, real life examples as well. So what do you think, like what is a big system? So you guys can imagine how big a system can be. Like think about a solar system. So there are more, far more bigger systems than solar system, right? So it gives us a appreciation about the size and the quantity, uh, and also the magnitude of the measurement and things like that. So if you look at the size itself is a parameter. So these are the books which are available for our kids in the schools and all that, right? So art is like kind of similar to the size of Venus, probably looks like in this picture. So and then the size of the sun is bigger than all of that, but it's really not. So it's way bigger than that can be represented in this screen. So the appreciation of size is really different. Or if I talk about direction, like if I ask you where is north in this, so you guys maybe like it'll take a while to figure it out where is north. So and what about temperature, right? So temperature is also one of the scale that measures, but I don't think so. There is a single scale which can measure the temperature from Uranus to the Venus. It has to be multiple different kind of scales which will measure different temperatures at that particular range because the range is so huge. Having said that, I wanted to talk about a project that's carried out by NASA during 1960s and 70s. Have you guys heard about the project Voyager? Anybody is there in the call who has not heard about Voyager mission? Okay, I cannot see hands, but then I assume like everybody's heard about that. So I just want to talk about the size and the magnitude of the problem. So if you see this smaller little sparkle dot here where my mouse cursor is, that's our sun. And this small circle is our solar system, right? Where we have Earth, Jupiter and all that. And then this blue circle is the area of influence of our solar system where the gravitational force acts upon on the solar system. Probably the sun is pulling things towards it, and then our planets are pulling things towards each other. The influence of that particular force is denoted by this blue sphere. And then also the direction, right? So the solar system is moving. So, and then if you see this gray kind of, elliptical surface, this is the three-dimensional space where our solar system moves. So basically, it's moving from left to the right directions towards these arrows. Now, the Voyager mission is about throwing that satellite out like to the interstellar. That means it has to go out of the Earth. It has to go out of our the boundary of the sun and then its gravitational influence, and it has to go out of our galaxy as well. So so this picture is very simple. It does not really interpret what is the size of the problem we're talking about here. So if you look at this nice color things here, this is interstellar, which is outside of our solar system. It may be somewhere in the galaxy. So this is a Voyager satellite. So we wanted that satellite to go out of the Earth atmosphere, then go out of our all of the um, yeah, solar systems, big forces like Jupiter, Saturn, Uranus, Pluto, Kuiper Belt, and all that. Okay, so it has to go out, and then it should go out of that direction, and then it should go opposite to the direction of the solar system is moving. then it is possible to go out of that surface. Otherwise, it'll be like moving around somewhere. So it may be like revolving around sun. It may be like revolving around some other big satellite inside some place, right? So the project was basically to solve the problem of the path. So what is the trajectory we need to traject, and what is the force, and what is the time, what is the direction we need to traject, so that that small little satellite goes out of our solar system. So there was a mathematical problem to solve. It's called three-body problem. So three-body problem is basically like if you read about geometry and calculus a little bit of, then you will find that you can predict different parts of three different points which are like restricted by some parameter. So in this case, these three points are basically restricted to the distance of the midpoint where it is revolving around, right? So there's a center on that point is fixed, and then other 3 points are basically moving around, and then the distance between the center and these 3 points are kind of restricted. So that's the reason you are looking at different graphs here, like curves. So now mathematically, how do we, predict the path? What is the exact path we need to, traject? So for our solar system, this problem is a little bit more complicated. So for a three-body problem, let's say we have Earth, we have Sun, like the red one is Sun, and then you think about that green ball is our Earth. Now, let's say I'm trajecting out that blue line, which is our satellite, and what is the direction I need to traject out so that it will go out of our, influence of the force which is act upon by Earth and the Sun. So I haven't considered about Jupiter. I've not considered about other satellites, right? It might, spoof around inside the Kuiper belt as well with a lot of asteroids. So just simplifying the problem here, just to scale it down and then try to understand what can be the, what can go wrong when I traject something out of the Earth. So the path is not really a straight line. It is like a zigzag, circular, elliptical kind of path. Okay, and then it's moving all around the places in the space. So who solved that problem? Basically, NASA need to predict now what is the path I need to predict. I need to traject the satellite, and then what is the time, what is the day, what is the force I need to traject that line so that it really goes out of our solar system. So even then, if you think about a little bit of the problem, so there are a lot of forces acting upon that. Okay, gravity, and then interstellar magnetism, then temperature is one of the things, directions of other forces. I'll not go deeper into this. You can Google it. But there are a lot of other. This is basically an n-body problem. It's not like even three-body problem. So in order to solve that, at that point in time in 1960s, NASA thought this problem will take a lot of time to solve. We need to give somebody who is like a very young scientist. Michael Minovich, probably you guys heard about. He's a great mathematician who solved the three-body problem, and then he's scaled that problem up to n-body problem to solve this interstellar trajectory. So he basically solved the problem of gravitational slingshot, like you traject something from the Earth and then use the Earth gravitational force to spin that off with a more velocity to gain the velocity, and then use the gravitational force and then traject that out at a particular point, the time and the space. So this computer was built by him. It's a NASA's Jet Propulsion Laboratory computer built in with the help of IBM machines. It has like 70 different computers combined together. It has the highest processing power at that point in time in 1960s. So using this machine, they solved that trajectory problem. So now basically, now you just can imagine like what is the size it can grow, right? So scalability is really about the size of the problem, right? How if you solve a smaller problem, how can you project that out and then to solve a bigger system together? So it's about really that. So now coming to our, our world of software engineering and perspective of online applications in terms of how it grows. So what are the main possible, factors a system we can call that system is bigger than this one? What is how do we measure that? So I would say like there are many dimensions. If we are dealing with more data, like our data set is like 1 GB versus 1 TB versus 1 petabyte or whatever. So that means the data system is growing. The data is growing. Okay, that's one of the measurement criteria. You can say that. Like if we have more processes, like there are a lot of steps involved. For example, the assignment I have given you a few days back that has seller seller is uploading his products. So you need to decide the price, then you need to upload the image, you need to configure the product, whether the other different options are available about the product, size, and then you want to bundle it with something. A lot of other steps involved. So more processes, it's more complex. Then we say that's more uh, bigger. The system is grown. So now more machines because basically physically you have a big hardware systems and then you have more hardwares. Then also you can say it grows. So why we grow all of that basically because we want to serve more customers. Our more users are using our systems. So that's how that's a basically bottom line of a system. System can grow, right? So guys, stop me if you have any questions or in between, right? Or if I'm going faster or slower, just give me feedback on the start. It's fine. So in order to measure that, so we basically measure the size. We size the data. We size the different processes and all that. Distance is also one of the things, geographical distance, right? So let's say my customer is in US and then my machine is running in Mumbai. Then that's a distance problem I had to solve. Or uses, like how many times a customer log into my system and then or how many times a customer use that product. So number of uses. Then effort. So basically how much effort is required to maintain that big system, how much effort is required to build that system, or just to monitor the system, and then if anything goes wrong somebody has to support, somebody to fix the problem and redeploy it. The whole process of maintaining and then creating the process itself is a big effort. So all of that criteria has been taken care. So when you talk about measurement of scalability. So in online systems, you might have seen these things, right? Server is busy, try later, or you see sometime, spinner is moving. So why? Because somebody has built something which is not up to the mark of scalability. So probably somebody is waiting for some process to be done or some steps to be done by somebody else. Because of that, you see all these messages. So this is because basically scalability problem, right? So let's define. So what is scalability? So what are the main parameters you can list out? Like if I have this, we can say that my system is scalable. So is it only because of high availability or only because of we have a bigger business to do? So scalability is not only performance or high availability or you have a lot of customers. It's also about traffic, what you get at a particular point in time. So it's about I think these are the most two important factors when you talk about scalability is a problem and that needs to be solved. So the data set and the size of the customers, size of the users of the system. So number of customers plus number of uses. These are basically multiplied to each other to giving that factor traffic. So now if I have a big system and then I have a lot of traffic and then I'm not able to cater to the need of the traffic, then how do I solve that? So if we can solve that problem, probably I'm solving the scalability problem. So if I do not do anything at that point in time, and then I have a lot of traffic, then I lose business, right? So it directly impacts my bottom line. Uh, now in this picture, I'm showing like if there's a lot of traffic, then I give another route. So I give a different path to support it. Okay, like let's say if you are in a bank, or if you are in a queue or different thing, then some other tailor will come up saying, hey, you can come here in this line. So there's a new line getting created. So we can support that way with a new resources or new infrastructure. So another way is saying, okay, I cannot serve you. So I'm only serving my existing customer, make that experience better so that they do not leave me, and then I'll stop with any new requests. So it's called throttling. So that's another way of handling scalability. So now this is about the experience part of it, right? So there are a lot of other way in terms of engineering we can handle scalability. So we'll talk about that a little bit. So uh, let's say talk about database, right? So we can split the database and in order to serve more customers. So there are multiple ways. One way is I can read from one database and then keep a replica to write, and then write in the other database, right? And then there is something called read write. So in order to write something, update something, I have to read the record and then after that write. So all these things we can split and then separate it out. We can have a master slave kind of configuration. So I'll talk about a little bit of ACID property here. So have you guys heard about ACID properties? Anybody? Yes, no?
I've heard of them, sir.
Can you tell like what does it mean?
Sir, I think they kind of specify some properties of a database like atomicity, consistency,
Mm-hmm. Yeah,
data integrity, and I think durability.
perfect. So atomicity, consistency, isolation, and durability, right?
Oh, sorry, isolation.
So
I thought it's integrity. Sorry.
yeah. So when we split a database, so we need to take care of that. Like if I have a master and a slave, if I'm reading something, and then I should be able to read the latest data. Okay, so that's a requirement. And that's called consistency. And then if I split the database into multiple shards, so something like this, I can have 20% users in a different box, different database system, or 25, like here in this picture, 25, like 4 different databases I have based on user IDs I have shared it. So atomicity will be consistent if a customer is only dealing with his own data, if he's not reading other customers' data, right? So in this case, atomicity will be taken care. If there's a problem here, so if a customer is reading other customers' data, let's say you want to run some machine learning algorithm based on something that needs to be read over other transactional data, which belongs to a different database, then the database has to be like consistent at that point in time, and then it has to be instantly available. The data should be instantly available. In this case, there will be a little bit of lag in the time. So we'll talk about it. So a little bit later. So now we can split the system in multiple ways, right? And then we can scale it accordingly. One is basically horizontal scaling, and another is vertical at a high level, right? So have you guys heard about horizontal scaling and vertical scaling? Any hands show up? Okay. So just moving on. Uh, I just kept in a tabular format. If I in the previous slide, you've seen like I split the data into two different ways. I kept same replica in multiple places. That's called horizontal. And then vertical is basically separation inside the object or inside the database itself. Based on different users, I have split it up, right? So that's kind of vertical. And also vertical also means like you do on the same product, basically in the same structure, and then and utilize accordingly. So these are basically high level difference. And then uh, so I would say like the main important point is this limiting scale, right? So vertical scaling is based on your infrastructure. You can have a big machine, and then you can have more memories. That's also limited, that you cannot have a unlimited scaling. But horizontal is unlimited. Now you can keep adding lot of machines, even if your machine is smaller. Let's say your Mumbai office is filled, and you can use your Delhi office to fill it up. So you can add like more machines in your Delhi office. So that's called horizontal scaling. So how much office you have, you can fill it up. In theory, there are main three different dimensions basically for scalability. We can think about as let's say we think about a cube, and then by different directions, x-axis and y-axis, if we can scale, or z-axis. So you can say like there are multiple ways. One is you can duplicate the data, or duplicate the whole thing basically. You can clone the whole thing. Like I'm running one web service in one machine, and then I clone it and run it multiple web servers. Then we call it like duplication, cloning the system. Not only the data, we can clone the service itself, or we can keep the data consistent one server, but that service can be cloned. There are multiple ways based on the needs. Now in y-axis, think about segmentation. Like let's say your processor has multiple steps. You create an order, then place a order, then the other customer might upload a product into your portal, like the problem you looked into, like a seller. So all are basically different actions or different jobs. I could say different segments. In this case, those can be separate microservices, or basically these are functionally separable components. We can put it in different web servers. Like one machine can handle order, the other machine can order, or basically handle the login. Different machine can also handle status of the order and all that. So those are separate microservices. We call it like decomposing the whole product and then doing it. That way we can have infinite scales. So let's say that's one axis. The z-axis, let's say, consider about shredding the data, or you uh, can split the web server itself into multiple. So pods means basically these are Linux entities, Linux kernels, small kernels. Have you heard about Kubernetes? Okay, so basically these are Linux containers. You can inside one Linux box you can create multiple containers. So one container you can call like a pod. So now your processor can run in parallel in multiple containers, right? So those kind of boundary splitting, or like shredding the system, is also called like partitioning. Yeah, I'm partitioning the web server here. You can also partition the database, like the example you saw before. Okay, I'm not going to very much detail about this. There's a good book which is describing this one, The Art of Scalability. I highly recommend you read that book. Uh, I'll share in the last slide what about the details of the book. So there are different pros and cons. So if we basically duplicate and clone it, so these are cons, right? So it is basically a hardware cost. Like you're buying more machines, and then scalability, because you have multiple data sets now, and then you need to basically horizontally take care of different replicas. And then it doesn't address caching. It's a very important point. Caching is basically for performance, right? So you do not make a DB call every time, and then you have a cache layer where you read the data from cache, because the data in the cache and the DB is same. So these things is not taken care when you duplicate the whole system. So decomposition in y-axis, we talked about decomposing into multiple microservices. So if it is lot of microservices, then you need to have a lot of teams working in different microservices and maintaining, and then maintaining different services, maintaining different employees. It's not very cost effective. Okay, but it is required if you have a very bigger system. Otherwise, you'll not be able to scale. So again, the complexity increases here. That's because you have multiple services. One service might call another service. That service might call another service. You can have a lot of transitional dependencies, and also sometimes you might end up creating loops. So architecture needs to be created very carefully in this case. The third one, we talked about partitioning. So partitioning is basically uh, the starting the data, or you can have different pods. In this case, also you need to architect it carefully. And then one good thing is here, basically you can use the cache because you have one machine running, and then inside that machine you have multiple pods. Again, that same machine you can replicate, but still you can have one cache running in some common bus or common cache like Redis or something.
Sir,
Yes, please.
how is y-axis different from z-axis?
Yeah, so y-axis, if you look at this is functional decomposition, right? So you talk about the total feature. Think about Amazon. So some sellers will upload a product and buyers will buy it, right? So
Yeah.
functionally decompose. I can run my seller service in a different microservice altogether, and then I can run my buyer service or order management in some other service. So functionally, I am decomposing. Okay, but so here in this z-axis, we are doing partitioning. So I'm having the same database, but I am partitioning based on users. Or I have a same
Okay.
server running. I'm partitioning the same processes to run it parallelly. So this is not a functional decomposition.
Okay.
Okay.
Yeah.
Okay.
Thank you,
Cool.
sir.
So yep. So have you guys heard about CAP theorem? So if we partition, or if we just do microservices like this, we basically run out some problems. So CAP theorem also states one of the problem. Anybody? Show hand. So we talked about acid properties, right? So CAP theorem is kind of interrelated to that concept. But at a very high level, CAP theorem says that, let's say if you are running, there's another theory called Breuer, right? So another person called Breuer. So according to him, like uh, if you have multiple teams working in a product, and then the way those teams talk to each other, so that's called Conway's law. That the way the team talks to each other is the same way they write their interfaces. So basically, if you look at the code, and then if you look at the teams as a human, the way they communicate, their code also communicate to each other similarly. So that's basically makes an impression in terms of human communication styles. It is tightly related to the organizational scalability. So when you grow an organization, so there's a certain horizontal enterprise level architecture needs to be defined. Or when you decompose something as a big product, and as an architecture level, enterprise architect, it's called enterprise architecting. So where you decompose different things, and then how do you define different contracts. So that's another aspect to look at in terms of scalability. So now at the product level, so when you want consistency, availability, partitions simultaneously, and then you really cannot do that in a distributed system. So this theorem really says that it is nearly impossible to do it simultaneously. That is because you have split the thing already. You do not have a relational thing in relational thing. So the relation is basically kind of a metadata you have abstracted out. This is also called Breuer's theorem. So for example, let's say you have a relational database and a NoSQL database. So do you guys know about the difference? Relational database and NoSQL database?
Yeah.
Okay. So for example, DynamoDB or Cassandra, these are like NoSQL. These are like tree structure or heap structure. These are document based data structures which are being stored. And relational is basically two-dimensional or three-dimensional or maybe a multi-dimensional database. But you really have a row column kind of concept. So in this case, the CAP theorem says that like if you have a very distributed system, it's really hard to maintain that, right? So now this document, think about a document database. The document database is basically kind of taking care of the consistency and availability. So if you look at the total difference here, so like consistency, availability, and partitioning. So when you partition the data, you need to have a certain tolerance limit. Like what is the time gap of consistency, and then how much time the database query needs to travel from one place to another to get the data from the other store. So it considers all of that. So based on these requirements, we need to really decide we want to go for a relational database or we want to go for a NoSQL database, or we want to strat the data based on the users, or we want to have a more replica, like same database but different replica, depending on these kind of requirements, right? So think about a transaction. Let's say a credit card transaction is happening. So I'm swiping my card. I have some card like ICICI, but that is again Visa, right? So I swipe for ICICI in some machine, and then it also talks to Visa, and it comes back, and you also go to my account and it checks. Let's say my bank account is with somebody else, right? So there are a lot of communication happens. So in this case, consistency and availability is very very important. Probably, NoSQL database is not a good example for this. Uh, but in other cases, think about the Facebook profiles, right? So you really have connected to different friends, and then friend of friend, and all, right? So kind of a graph structure. So does it make sense to keep those things in a tabular format, and then your read query will be very complex, and then you might need to read a lot of rows in this case. But if it is already a graph structure database, then probably it will be easier to find out the nearest connected profiles of a particular node. So in this case, like NoSQL database makes more sense. Okay, so far so good. Any questions? Okay, we have 20 more minutes. I'll quickly pass through. Okay, so I just want to give example between Amazon and Alibaba. So the size of the business is kind of a little bit bigger in Amazon, but the size of customers are very high in Amazon. Also, kind of revenue and all that, right? So if you look at like total number of customers visited Amazon in a particular day, let's say big billion day. So I found in the internet saying it's a 2.2 billion one day customers, and then Alibaba has multiple websites. Like these different boxes are different websites, and then they have like close to 800 something million per day. In any case, both needs to have very scalable systems. We'll talk through about this use case, like let's say 2.2 billion customers. Now, in order to serve 2.2 billion requests in one day, that is 24 hours, let's say roughly. what is the speed of the machine I need, right? Or rather, how many machines I need to serve that request. Okay. Let's say so I want to have a very scalable infrastructure, and then I want to support 2.5 million requests one day. Then what is the request per second you need to support? Can anybody calculate quickly? So what should be the request per second if I want to support 2.2 billion requests in one day? Like 2.2 billion divided by 24 divided by 60 divided by 60, right? That many. Anybody got that number?
Sir, around 25,000 something.
Yes. So exactly 25,400 requests per second I should be able to support in order to support
Yes.
2.2 billion requests, right? So now,
Right.
if you at a current date today, so it's like 21st century, right? We do not have a machine which can support that many requests at 1 second. We might build it, but if you buy from market, you do not really get it directly. So AWS has machines which can support 10,000 requests per second, which is like 3 times lesser than that. So how do you support that request, that many requests, right? So you have a lot of requests coming, but you can support only this many. So the first thing you will think that, okay, I'll run 2 machines or I'll run 3 machines, right? Now you have a website and then you have only one address. So how do you do that? So like you are running 4 different machines and then you have only website one. Then a request is coming there. Then how do you do that? So you guys heard about domain name service?
Yeah, actually, it maps the website address to the IP
Yeah,
address, right?
exactly. So let's say your browser making a HTTP request, and then uh, uh, the website name is, let's say, example.com, and then I'm using AWS clouds server where my web server is running, and then let's say my web server is running in an IP address of 1234. Okay, so now how that gets mapped, if how the customer's browser knows that this is the machine I need to reach, right? So generally, let's say my website is okay, but generally, let's say my browser is running in some internet provider. Let's say I have an Airtel connection, right? I just did like www.example.com. It will go to my Airtel internet service provider DNS resolver. So Airtel will be running a DNS resolver server. So that server will basically take the first request, and then resolver will say, okay, you need this one. So okay, go to the root of root name server. That also belongs to Airtel. So Airtel also will run another machine called root name server if that guy has this address. So the root name server will say, hey, no, I don't know. But I know .com. I don't know about example, but I know about .com who supports .com. So it'll go to your .com name server because you have .net, .com and all that, right? .org, .edu and all that. So this root name server knows who is the .com server. So then resolver will go to the .com server, name server, and then it'll ask you like, I need example.com, who has that? So this guy will say, oh, I do not have it, but I know who has that. So it will say, okay, this belongs to AWS, so you should go to Route 53. So Route 53 is a DNS service run by AWS. So when you register your domain, you need to tell AWS that, hey, this is my example.com is my domain, and then I'm registering then please map my IP address with that. So he will map it. So when you register the domain, you tell that, hey, I want a .com domain or I want a .org domain. So in this case, your name server, .com server or .org server will know that, hey, this is my address, or who has the address basically. So then your Route 52 say, yeah, I know about this. So this is running against 1234 IP address. Then basically your browser will get a request from Route 53, and then eventually your web server will map to that IP address. Okay, so please remember that .com server needs to be registered when you are registering a domain. Then that server knows that this is the domain that belongs to AWS or Yahoo or Google or whoever. So when you register, you make two entries. One is basically the example .com, that will be basically your name server, and then if it is a .com or .org or whatever, that will go to that server basically, name server. So based on that, those mappings will be resolved. Okay, so Route 53 is one of the very important service. If you guys learning about cloud computing or cloud infrastructure, then if it is AWS, obviously Route 53 will come into picture. So it is a very available, like they guarantee 100% SLA. That means Route 53 is always up and running, so it will never go down. Okay, so now I want to build my scalable example.com. Then probably I need all of that, which is like minimum. This is kind of a little bit complicated. If anybody knows AWS here, a little bit of. I guess no. So I'll quickly, I'll not go over everything. So Soumi, I'll share the video. Probably you guys want to see this slide and then Google it, what each of these small pictures does mean, and then what it does, and what is it used for. So I will talk about the auto scaling group and then availability zone, right? So you see these dot lines, AZ1 and AZ2. So these are availability zones. So what happens in infrastructure when you give the service like one of AWS or Google Cloud? What they will do is they will replicate your system, the whole system. Like you have web server, app server, database, and all that. So they will replicate the whole thing, and then they will run in multiple places. Like one is in Mumbai, one is in New York, one is in London, whatever they have. So you can basically define it. Tell them like I want to run my service in New York and London based on my customer base. Let's say I have more customer in UK, then I will run in London, or I have more Indian customer, rather I will run in Mumbai or Singapore, wherever. So I'll choose my availability zone, and then in one availability zone, I'll have to create one VPC. It's called virtual private cloud. So this black dot is kind of one VPC, and then there I'll basically group, right? Sorry, this whole thing will be one VPC, and then these are different groups. So auto scaling group is basically it'll scale up. Like you get more requests. Let's say today I'm getting like 200 requests per second. Let's say I have a big billion day running, then I'll get like 25,000 requests. Then what will happen is once the request coming in, the system will automatically scale up. It will create more web servers. Now you see two, it can create 20, or your app server will also get like 20, whatever. So it can also do have more cache. Then your DB will also scale in this case, but then you have to configure to scale your database. So in this M is basically master and S is slave, right? So slave is just I'm reading it from one and then writing it to another one. So and then in terms of availability zone, let's say you have availability zone, multiple availability zones, then your DB will also get replicated. So Amazon or AWS will automatically copy your data from one availability zone to another. It automatically sync. Let's say one guy goes down, then other guy takes over. So all of that traffic management will be taken care by Route 53, that your DNS service, right? And then you have something called load balancer, elastic load balancer. So load balancer will take care of load balancing the traffic. So let's say I'm getting 25,000 requests per second, and I know one server cannot handle. So auto scaling group automatically scale up based on your load balancer requests. It'll throw more requests to this server, and then you'll see that, oh, okay, I'm getting the threshold now. Then I'll spin off another machine here, and then I'll ask this guy, hey, now you can give request to this guy as well. So he'll start giving it here. So that's how the auto scaling works. And then it'll also scale down. Let's say in some festival, Holi or Diwali, I get more requests. Then it'll scale up, and then after Diwali, there's no request or very less request. Then it'll scale down. If it scale down, your cost will go down of the total whole setup, right? So everything is basically service based. If we use more, you pay more. So I'll be using lesser, then auto scaling will basically scale it down. So again, this DynamoDB is required in terms of if you have some NoSQL requirement and all. So S3 is a static container, like static storage, data store, like image files or like document you can store here, or like KYC. Let's say I want to do KYC, I want your PAN card or photo or whatever, stored in this kind of store. Then CloudFront is for monitoring. You're running a very complex system here. You want to monitor, you want to know what goes wrong, and then you want to alert some of your developers or some of your engineers. If something goes wrong, they can come and quickly fix it. So because of that, you need some system, right? So CloudFront is a system where you can log. So every request will get logged here at every different steps. So based on that log, you can create some tools. I'll quickly show as well. So we spoke about all of that. Yeah, so this architecture is taking care of CAP and ACID as well. So time check, we have 30 minutes. So we talked about scale up and scale down. So okay, so what do we do it Intuit to scale? So as you know, probably Intuit has like two predominantly bigger scalable products. One is QuickBooks, which is basically dealing with small business accounting and payment and finance. Then other one is TurboTax. TurboTax is basically tax filing software in the US. There's a lot of customers. So I think 90% people in US file tax using TurboTax. So during tax seasons, we do support a lot of traffic. And then these are not like buying something like in Amazon you buy a phone and then you're done. But tax is something you multiple retry, you have 1099 W2 because it's very complex. And then you know talk to your tax consultant as well. So this app also provides communication between tax consultant and the taxpayer. So it's very heavy weighted communication, and then it also involves uploading a lot of documents, your financial documents, bills, and all that. I know for tax, same as QuickBooks as well. So QuickBooks is accounting. So you need to upload documents, you need to scan documents, you need to extract different data from a document, and then create transactions, then payment, into take care of customer, vendor, and all that, right? So we have a lot of different domains. So in order to scale, what we did is basically at enterprise architecture level, we broke down all of that into different small pieces. We call that like decomposed domains. Let's say customer, accountant, and all that, developer. So developers also can create services, right? And then they basically create different plugins, UI components, and all that. So for that, we need to cater to the need of the developers as well. That is also another domain. So let's say customer, there's a separate team who is working on that. They work for customer experience. They work for customer is managed, how customer is managed inside QuickBooks or inside TurboTax. So this is how we break down this domain, and it's really complex. So I haven't included everything, but at a different level, right? At Intuit, developer platforms. We have developer platforms. Then after that, we have data and then intelligence systems and all that. Then we have ecosystem, integrate it, functional capabilities where we have globalization, billings, and all that. So globalization is basically, if you want to launch a product in one country, then how can you cater that same product to multiple countries? Like translation is one of the thing. Then compliance of that country, or like tax filing is a different logic in US and India separately, right? So how do you take care of that different delta logic and then do it uh, in the same product? So globalization is a domain where these things even taken care. So every domain has a separate important work, and then they deal it diligently, and then everybody is like horizontal. Okay, so that's all about how do we break the product. So now we break the product at the front end level as well. So let's say you currently QuickBooks.com, or you go to TurboTax.com. Now, if let's say one service is down, or one domain, like any service is down from here, then the whole product will not be, non-available. It will be available, but only one component will not be available, which may not be visible to the customer. So that's one of the benefit of breaking down things into smaller pieces and then partitioning it. So we do that for the front end as well. Like the whole web page can be broken down into multiple segments, and then each front end, will be served by a different microservice, or like one microservice in combination of that. So when we separate those segments, when you check in the code in the GitHub, let's say one component, this is basically one component is handled by one team, let's say, for example. And then this yellow one, like I am releasing micro frontend A, that is supporting by microservice A. So source control is GitHub. I check in the code, and then my build pipeline automatically kicks off. And then it knows that somebody has checked in the code. It'll start building it. It'll run the tests, automation tests on that, and then it'll deploy in the production, right? So now every team will do the same. Let's say this guy is releasing on Sunday. He can do it on Monday. He can do it on Saturday or whatever. So now ultimately the product will be visible in few minutes. Basically, the whole thing takes care from here to here. It takes like more than 10 minutes, 10 to 15 minutes, right? That will be visible automatically. So how do we manage the teams in this case? So let's say we have a product like a front end. We have forms and validation and like HTML, CSS, and all that, right? So the one team takes care of the whole thing, like one component. So we do not have a team like who is horizontally doing, like somebody's only doing CSS in multiple products. We do not do that. There's no cross domain kind of thing. But the domains are being separated in order to make it faster, releasable, and then independently they can take a decision about that. Product management and product marketing take care of those features separately, and then they give a lot of autonomy to the team. That's how they can move faster. Okay. So moving faster is also one of the important factor of scalability. So that basically comes down to operations. So when you say operations, it deals with a lot of things. So now I have launched my product, I've released the product, and now what? So I have to support my customers, I have to support my developers, or I have to support my stakeholders, and then for that I need to create different monitoring systems in order to monitor my systems when it is running in productions, and how my customers are doing about that. So for that we have something called DevOps. So DevOps is like developer plus operations, right? So it's kind of a relatively new concept. So where we do things continuously, start from planning and then collaborative development. We get the requirement and then we make a thin sliver, and then end to end we develop a small minimum viable product and then release it. Then we do testing and then release it. We also monitor that small piece, and then we just continue that. So most of the things are automated as much as possible, and then we call it like CI/CD. So it's called continuous integration and continuous deployment, right? So I'm just showing a live example of CI/CD pipeline, how it looks. So are you guys aware of CI/CD? is it like part of our software engineering course or something?
Sir, could you repeat your question, please? Sorry for that.
Have you heard about CI/CD?
Continuous integration and deployment
Yeah.
is
Is it part of your course?
not in second year, sir. Not for me, at least.
All right. I think it must be there in future probably. So it is very important. So where it gives you a fast track development lead time and then deployment lead time as well. So when a feature comes, you develop it, and then your team's also being developed parallelly, and everybody's checking in the code in GitHub, and then it takes from GitHub to your customer's product. Everything is automated end to end. So you can use some tools which are already available in AWS. You can create a student account which is free. You can try, creating, pipeline. Let's say you can use GitHub. So I have shown like AWS code commit. Instead of that, you can use GitHub as well, or servers, anything like Bitbucket is also. So once you check in the code, uh, you get to deploy the whole thing to your EC2 instance. Like these are basically Linux machines or Windows machines, whatever you can create. So it does it magically. You can have a look in this slide. So probably you can Google it. Okay. So basically, ultimate goal of observability is basically uh, is to maintain the infrastructure and then maintain the IT availability. So so that you can support the product and support customers whenever they need immediately. So for that, into log, so create logs, and then use monitoring tools, then create reports, and then alert it. Like alert meaning like you send an SMS and an email to somebody so that they can react. So, for example, we use something called Webfront. That's a tool which is integrated with our product. Uh, it it basically gives the data about memory, different errors you can log. Another tool called Splunk. It does a similar thing, but it is more like a a debugging kind of tool, and then this one basically more like a system side health. Very important tools that's been used. So I'll basically stop here and then we'll see any questions. Any questions, guys? So I guess no. Probably what I'll do is uh, you can Slack if you have any questions and all. We can talk about the Slack as well. And then there's a next session on scalability, and then there are two assignments what I gave you guys, right? So if you have like 5 minutes time, probably you can talk about that. Soumya, is that fine?
Yes, Rana, we can provide a high-level overview for the first solution.
Okay. So let me bring up that. I think people have attempted doing good that they have attempted, but then looks like one of them has done it correctly. But then I'll just give a hint, okay? We'll see if we can solve it together. That was in Slack, right?
Yes, that's right.
Okay. So okay. So this is about quicksort, right? So quicksort. What is the worst case complexity of quicksort?
N log n.
Big O of n square.
Yeah,
N
At
it's n
square.
the
square.
n square. Worst case,
Worst
it's n
case is
square.
square.
Yeah. Okay. I think that's the mistake you guys did. So that is the reason I gave kind of an optimistic view here. It says like half of them are mispredict. Like, you can assume that I'm not expecting n square complexity, so it is like log n, right? Uh, so what is the worst case basically? So how quicksort works?
The
When
worst
can
case would be when it's already
Mhm.
in sorted order.
uh is it? So
Or you can
okay,
say
how
the
quicksort? So it works on partitioning, right? We talked about partition a lot in our talk, right? So quicksort is one of the example where it partition the data. So you have a big array
Yes.
and then you partition the data and then inside that partition you do a sorting, right? And then swap it. So let's say you have an array of size n and then what can happen is you have a very big partition and then one partition is very small. Let's say n minus 1 is the size of the one partition and other partition has only one element, 1. So in this case, that's a worst case, right? Because you need to have now, n partitions. So because n into n, that will become n square. That's the worst case. Clear? So now 1 GB data of 4 byte numbers. How many numbers?
2 for 28.
2028, right? So if we have 2028 numbers and then now your these anyways, so these many numbers and then you have so okay, let's open anybody's answer. That'll be good, right? So this problem has two phases basically. One is uh, when you are processing the array using quicksort, and other is basically when you transferring the data. So transferring the data from memory to the CPU basically. Yeah, this was closer, but then okay. Let me tell you. So let's say we have half of them are mispredict, right? So in this case, uh, we'll have 2 to the power 32 total computations. So which is basically 2 to the power 32 into 5 nanoseconds. So you have 5 nanoseconds, but this is it has to be 2 to the power 32. It's not 31. That's the thing. Because half, right? Half is divided by 2. So log of 2 to the power 28 is 28, right? So that many passes over 2 to the power 28 numbers. So that many basically how many passes? How many comparisons total? So 2 to the power 28 log of that is basically 28, and then you have 2 to the power 28 numbers. So that means basically 2 to the power 33 is the total number of comparison. So half of that is basically 2 to the power 32. So 2 to the power 32 into 5 nanosecond is the total time to compute, which is like 21 seconds. Are you with me? And the computation is 21 seconds, guys. Did you get that answer? Okay, the other part is the transferring the data. Okay, so here it says I'm doing a sequential pass. It is no parallel pass. It's just sequentially I'm passing. That means 2 to the power 30 bytes of data, which is like 28 passes. Like I have 28 segments or partitions. Then basically it is 2 to the power 30 byte into 28 passes. Basically 28 GB data I have to transfer. Right? So if I need to transfer 28 GB, then 4 GB in one transfer. That's basically just 1 second. 4 GB transfer takes 1 second, and how many second it is required to pass 28 GB? Hmm? 28 divided by 4.
7.
7, right? So here we got 21 second, and here we got 7 second. So total answer, I think you missed the 7 second. That's why. The total it will be 30 second.
But I guess the data is not of 28 GB. They are 2 to the power 28 numbers, no?
Yeah, 2 to the power 20 numbers. 1 GB data. See the question?
Okay.
Okay. So, but when you are transferring to the memory, you have done partition of 28 different type of partition, like so that is the reason you have to pass that. So 1 GB into 28, like it will be 28 GB total. So you have to stream 28 GB data from memory to your CPU or whatever. So there's a reason it will be 7 seconds.
Okay. Okay.
Okay. So now this question, API, yeah, correct. So this question probably will. How do you want to answer this question now? Now, since you know a lot of terminology and a lot of technology in scalability, right? So how do you want to rethink about your solution, and then how do you want to architect the second problem? Let's say you want to have a seller central kind of a portal where seller comes and then upload the product, and buyer go and buy that, and then you want to scale it up, like you need to support any product, any seller, and then you need to support buyers from different regions, different places, geographically, right? So how you want to make it scalable? Probably the architecture, what I presented here, you might want to think about this kind of architecture, right? And then how do you want to propose a solution for that? Probably you can write it out. And then we can also discuss in the second session as well. Probably, Somya. So, are you going to take that in the second session as well?
Yes, Rana, I think we'll cover solution to the second question in the next session and any other examples that we'd want to share with the students and also brainstorm a little bit more for them to understand how to basically design at scale.
Okay. Okay, cool. So, yeah, so I think that's all for now. If you have any questions, please drop a Slack note. I'll be able to respond.
Great. If we don't have any more questions, we'll close the call for now. I'll also share Ranadeep's Slack ID on the channel so that you can get in touch with him directly if you need to ask any questions. So as a guideline for y'all, what y'all could do is in order to help with the first question that Rana talked about, you can work with your mentors as well to see how to come up with the solutioning to be able to understand it better. And for the second question, as we said, we'll cover it in the next session that is going to follow next. Okay then. Thank you so much, Rana, for taking time and taking us through this session. It's been really insightful. There's a lot of data over there and a lot of resourceful material.
Yeah, sure.
So we'll share the recording.
Okay, I will also look forward for feedback about the content and about the presentation as well. Like any feedback the participants has, please feel free to Slack or pass it to Soumya. It'll be helpful for us as well.
Absolutely, Rana. So if you have any feedback, guys, please do share it with us. All right.
Cool.
Thank you and have a good evening. Thank you so much.
Yeah.
Thank you,
Good
ma'am.
rest of the
Thank you,
day,
sir.
guys.
Thank you.
Bye.
Thank you, sir.
Bye.